What if the very mathematical engine that makes artificial intelligence so incredibly smart, I mean, the core code powering this entire AI revolution, is actually the exact same math that guarantees it will eventually suffer from permanent digital amnesia? Think about that for a second.
Yeah, it's a wild thought. Because, when you sit down to learn a new skill in the real world, say you decide to finally learn how to play chess, you don't suddenly forget how to tie your shoes.
Right, exactly.
The human brain is additive. We layer our knowledge. You build a brand new, highly complex cognitive model for chess strategy. But those deeply ingrained neural pathways that control tying your shoelaces or making your morning coffee, they remain completely intact.
But in the world of artificial intelligence, specifically with these massive neural networks dominating every tech headline today, that is exactly what happens.
Oh, entirely.
It's as if the moment the machine perfectly memorizes the rules of chess, its ability to tie its shoes is just wiped from its memory completely.
Just gone.
So, welcome to the deep dive. Our mission today is to explore the absolute cutting-edge foundations of generative AI. We take stacks of sources, research, papers, and we distill the most crucial insights for you.
And today's a big one.
It really is. Today, we are laser focusing on one specific, highly provocative paper from Arcadi Labs. It's titled The Art of Not Forgetting.
Which is such a great title, and it genuinely challenges the bedrock of how we currently build and train AI models. I mean, it asks us to reconsider the entire foundation of machine learning.
And look, whether you are actively building neural networks or you're just a listener trying to keep up with the overwhelming, chaotic speed of AI breakthroughs right now, understanding the memory of these systems and mechanically why they fail is just crucial to knowing where this technology is heading next.
Absolutely.
Okay, let's unpack this. Before we get into the radical solution Arcadi Labs proposes, we need to clearly define the flaw in the machine. We hear the term catastrophic forgetting tossed around a lot.
Too much, maybe.
Yeah, probably. So let's break down what that actually looks like under the hood.
Well, catastrophic forgetting describes a very literal phenomenon. When you train a standard neural network sequentially, meaning you give it a data set to learn task A, and then you pack up task A and move on to teach it task B, the network tends to aggressively overwrite what it learned on the first task.
It just bulldozes it.
Exactly. The prior knowledge isn't just degraded a little bit, it is functionally gone.
So going back to our earlier thought, it's like trying to memorize a complex new recipe for dinner, and the physical act of learning that recipe deletes your knowledge of how to operate your coffee maker.
That captures the severity of it perfectly, yeah.
Yeah.
And historically, the AI engineering community has treated this amnesia as a training time defect.
Like a bug.
Right, they view it as a bug to be patched, so they try to fix it after the fact using these external mechanisms. One common method is a replay buffer, which essentially forces the model to constantly review old data while it's learning the new data.
So it's cramming for 2 tests at once, basically.
Yeah, exactly.
Yeah.
And another method involves regularization terms, and the most famous of these is EWC, or elastic weight consolidation.
Okay, wait, let me see if I have this right. EWC is basically putting mathematical guardrails on the network. Like, it identifies which pathways were important for task A and artificially stiffens them so they don't change too much or too fast when learning task B.
That is exactly the goal of EWC, yes. But Arcadi Labs looks at all of these methods, the buffers, the guardrails, and points out that they are really just Band-Aids.
They don't fix the underlying disease.
Right. They ask a much deeper question. What if catastrophic forgetting isn't a bug you can patch? What if it is a structural, unavoidable consequence of the core learning algorithm itself?
Oh, wow. So they are pointing the finger directly at backpropagation.
They are. Backpropagation is the engine of almost all modern AI. I mean, it calculates the error of a prediction and sends a signal backward through the entire network to update the weights.
And it's been the gold standard for years.
Decades, really. But the fatal flaw, according to this paper, is that backpropagation assigns credit globally and densely based on a, quote, single scalar loss.
Whoa. Let's pause there for a second. Single scalar loss. For the non-engineers listening, we need to translate that. What does a single scalar loss look like in plain English?
Okay, imagine grading a massive group project with 100 students working on it.
Okay, sounds like a nightmare already.
Right, so instead of grading each student's individual contribution, the teacher just looks at the final poster board and gives the entire group a single letter grade, say a C-.
Ouch.
Yeah, and that C- is the single scalar loss. The teacher then tells all 100 students to fundamentally change how they are working so they can get an A next time.
Even the students who did their specific jobs perfectly.
Especially them. The feedback touches every single person. So in a neural network, backpropagation touches every single weight based on that one global error score.
I see.
Yeah, if you are constantly rewriting every single weight in the entire network to minimize the error on your current task, you are mathematically guaranteed to overwrite the delicate weight configurations that were storing your past tasks.
So the argument is that backpropagation is functionally doomed to forget. I mean, by its very nature, it just has to destroy the old to make room for the new.
Exactly. To truly resist forgetting, the paper argues you need an entirely different architecture. You need a learning rule that is local, sparse, and gradient-free by construction.
If the grading system is entirely broken, we basically have to build a school without grades.
That's a great way to put it.
And that leads us directly into the architecture they built to test this wild hypothesis. They call it CMP, which stands for Cognitive Memory Primitive.
Right, CMP.
I want to spend some real time breaking down how this machine is built because they throw out the traditional AI playbook from step one. I mean, they start with a mechanism called sparse relational binding. Let's take that piece by piece.
Sure, let's compare it to what we know first. In a standard transformer model, the architecture behind modern chatbots, you have self-attention.
Right.
Self-attention looks at the entire sequence of data all at once to find context. But CMP rejects that global view entirely.
Okay.
It takes just two things, the previous byte of data and the current byte of data, and it binds them together through a multiplicative operation into a single sparse vector.
Wait, let me push back on that setup for a second. When we look at models like ChatGPT, they use massive subword vocabularies. They chunk text into whole words or like meaningful pieces of words to understand language efficiently.
Yeah, tokenization.
Right. But you're saying CMP is operating directly on raw individual computer bytes. Why zoom all the way into the byte level? Doesn't that make the model's life so much harder?
It seems counterintuitive, I know, but it's a very deliberate, necessary design choice. See, if you use a subword vocabulary with tens of thousands of tokens and you want to bind pairs of them together, you need a prepare lookup table.
Oh, and that would get huge.
Exactly. That table grows exponentially. A vocabulary of 50,000 tokens means billions of possible pairs.
That's unmanageable.
Right. So by operating on raw bytes, which only have 256 possible values, CMP completely removes the need for that massive exploding lookup table. It keeps the core operation fixed in size and completely local.
Okay, yeah, the byte level focus makes sense for keeping the math manageable. But let's talk about the binding itself. You mentioned a multiplicative operation into a single sparse vector.
Yes.
Again, let's make sure everyone is with us. Is a sparse vector essentially like a massive spreadsheet where 99% of the cells are left intentionally blank and only a few specific cells have numbers in them?
It is a brilliant way to visualize it, yeah. The binding multiplies the representations of those two bytes together, and the result is this vast grid, mostly filled with zeros.
And why is the blank space so important?
The sparsity is crucial. If representations are dense, meaning every cell has a number, they overlap. And overlap causes interference, which causes forgetting.
I get it.
Right, so sparsity ensures that different concepts light up completely different, non-overlapping parts of the spreadsheet.
But if it's only looking at 2 bytes at a time and making a sparse spreadsheet out of them, it inherently has zero long-term context. I mean, it only knows what happened a millisecond ago.
Yes, yeah.
So it must have some kind of internal scratch pad to write down past interactions. Otherwise, it couldn't understand a full sentence.
You hit on the core mechanical challenge right there. And their solution is the two-tier memory system.
2 tiers, okay.
Think of it as having a fast, highly reactive short-term buffer and a slow, deeply protected long-term register.
Buffer and register, got it.
When that new sparse spreadsheet is generated, it's used as a query against this memory system. But this isn't just a passive database. It is a highly competitive, content-addressed memory.
Competitive meaning it doesn't just let any random piece of data take up space in the memory bank.
Precisely. A memory slot in CMP will only fire or update if there is a genuine, significant match with the incoming query.
So it's picky.
Very picky. This is controlled by a strict mathematical match threshold. It completely ignores baseline coincidental overlap. And to move from the fast buffer to the slow long-term register, a memory code must survive repeated matching over time.
It has to earn its keep. Like if a concept keeps showing up, the system promotes it to long-term storage.
Exactly.
If you're listening to this and wondering why you should care about sparse spreadsheets and memory buffers, just think about the sheer elegance of this. We are building a machine that decides what to remember based purely on local, immediate relevance, not some top-down command.
It's a completely different paradigm.
But language isn't just pairs of bytes. It has deep structure. Phrases, sentences, paragraphs. How does a system that only looks at 2 bytes ever understand the bigger picture?
Through a fascinating mechanism they call hierarchy and predictive coding.
Sounds intense.
It's actually pretty elegant.
Yeah.
CMP takes those consecutive byte-level relational codes and binds them together again. This creates a coarser code.
Coarser meaning like zooming out.
Exactly. You can conceptualize this as zooming out from the fine-grained byte scale to a broader word scale.
So it's looking at the general shape of the data and then predicting the specific details from that shape.
That's the essence of the predictive coding loop, yeah. Once CMP has that coarser, zoomed-out code, it uses it to actively predict what the fine byte scale code should be.
And what if it's wrong?
That's the best part. The system looks at the difference between its prediction and reality. That difference is the prediction error, and it's kept as a vital learning signal. It is an entirely self-supervised, top-down prediction mechanism.
Okay, so all of these pieces, the bound sparse code, the retrieved memory from the register, the zoomed out coarse code, and that prediction error, they all get funneled into what the paper calls the readout layer.
Right, the readout layer.
And this is where the model actually makes its guess for the next byte. But here's the elephant in the room. We established earlier that CMP does not use backpropagation. If there is no global signal flowing backward to grade the work, how on earth does this machine update its weights? Like, how does it actually learn anything?
Through the local delta rule. The readout layer is updated using a local one-step mathematical rule based solely on the softmax error at the readout.
Softmax error. Okay, we promised to keep the jargon translated. What is a softmax error in plain language?
Softmax is simply a mathematical function that takes raw scores and converts them into probabilities that add up to 100%.
Okay, so like confidence percentages.
Exactly. So if the model is 80% sure the next byte is an A and 20% sure it's a B, the softmax error simply measures how far off that 100% confidence distribution was from the actual correct answer.
Simple enough.
But the critical part is what happens next. The update to the network's weights stops right there.
It doesn't travel back.
No. The update is one single hop away from the error, and it travels no further. There is zero backpropagation chaining through the layers of the network.
But wait, let's think about the logic of that for a second. If you use a local delta rule at the readout, aren't you just moving the forgetting problem to a different location?
How do you mean?
Well, a plain delta rule is still going to update those local readout weights equally hard, regardless of what task you're currently training on. Like, if it learns Shakespeare and then moves to Python code, the delta rule will still happily overwrite the local Shakespeare weights to get better at Python.
Ah, yes.
So how does CMP genuinely protect its past knowledge?
That brings us to the most vital component of the entire architecture, the weight protect throttle.
With a throttle.
Yes. This is the paper's one concrete, purely novel mathematical contribution to the field.
Let's get into the mechanics of it. How does the throttle work without using backpropagation?
We need to look back at EWC, that regularization patch we discussed earlier.
The guardrails.
Right. EWC relies on calculating something called Fisher information to figure out which weights are important and shouldn't be changed. But the fatal flaw there is that Fisher information fundamentally relies on squaring a backpropagated gradient.
And since CMP banned backpropagated gradients by design, they are completely locked out of using EWC.
Exactly. They had to invent a gradient-free importance heuristic. And their solution is remarkably straightforward. CMP simply tracks the raw magnitude of weight movements across the training process.
Raw magnitude of weight movements, meaning what exactly?
They look at the tensors, which is really just a formal term for the multidimensional grids of numbers that make up the network's weights.
Okay, the number grids.
Right. After training on a specific domain, the system calculates the mean absolute movement of each tensor. It literally just asks, how much did these numbers change while we were learning this task?
Oh, wow.
And that movement is accumulated as an importance score.
Oh, I see where this is going. If a specific local neural pathway was heavily utilized, meaning its numbers shifted around a lot while learning the works of Shakespeare,
Yes.
the weight protect system essentially slaps a bright yellow do not erase sticky note on that specific pathway.
That's exactly what it does. A physical throttle is applied. Future updates to those specific weights are mathematically scaled down.
Yeah.
They're inversely proportional to that accumulated importance score.
So it literally can't change them as fast.
Right. It physically restricts how fast that pathway can change when the model moves on to learn something completely new.
That is wild. It protects the structural integrity of past learning from the ground up without ever needing a global teacher to tell it what to protect.
It's a completely bottom-up approach.
Okay, so on a whiteboard, this gradient-free, locally throttled architecture sounds bulletproof. But theory often falls apart in the cold reality of the lab. How do they actually prove this doesn't just forget everything the second it reads a new data set?
They subjected it to a grueling, continual learning showdown, CMP versus a traditional transformer. And they made the conditions incredibly strict.
How strict?
Well, they used a domain incremental protocol across 15 radically diverse text domains. We are talking Wikipedia articles, CPython source code, the complete works of Shakespeare, the King James Bible, Reuters Newswire, all the way to a Hindi text corpus.
And the constraints are what make this test so brutal, right? Because there is absolutely zero replay allowed.
None.
Once the model finishes reading Wikipedia and moves on to the Python code, it is never allowed to see Wikipedia again. Furthermore, there are no task identifiers.
Right. The model is not told when the topic has changed. It just suddenly starts receiving Hindi instead of Shakespeare, and it has to adapt on the fly.
That sounds impossible for a standard model.
Those constraints are vital to proving the paper's thesis. No replay and no cask IDs mean that anything the model manages to remember must come directly from the physical architecture itself.
Not from being artificially reminded by the researchers?
Exactly. And to measure this memory retention, they use a metric called bits per byte, or BPB, with a specific focus on a submetric called backward transfer, or BWT.
Okay, before we reveal the final numbers, we have to explicitly define the sign convention here because it is entirely backward from how we usually think about test scores in school.
It can be confusing, yeah.
Right. So in this specific BPB metric, a positive BWT score actually means net forgetting. It means the model got measurably worse at older tasks after learning new ones. A negative BWT means genuine backward transfer, the holy grail, where the model somehow improved on old tasks after learning new ones.
Yes.
So in this test, lower is better and positive numbers are bad.
Keep that in mind. So they ran a match-size transformer, about 6.5 million parameters, through the 15 domains using naive fine-tuning, meaning no memory mitigation at all.
Doing baseline.
Right. The baseline transformer scored a BWT of positive 2.7897, massive catastrophic forgetting across the board.
So they gave the transformer its best possible defense, the online EWC patch.
And it improved, but only slightly. It scored a positive 2.2457. The amnesia was still severe.
Then they tested their gradient-free CMP, and they matched the data budget perfectly, exactly 3.8 million bytes per domain, so everything is mathematically fair and isolated.
Yes, a totally fair fight.
And the CMP architecture scored a BWT of positive 0.1482. Here's where it gets really interesting. Think about the scale of that difference. A transformer with EWC scores 2.24. CMP scores 0.14.
It's massive.
CMP forgets 15 to 19 times less than the transformer baseline.
It is a stunning empirical validation of their core hypothesis. I mean, a local, sparse, gradient-free architecture with a movement-based throttle structurally resists forgetting in a way that backpropagation simply cannot achieve, regardless of how many patches you apply to it.
That is an absolute landslide victory for CMP on the memory front. The numbers don't lie. But this raises a glaring question. If I'm listening to this, I'm wondering if this architecture is 19 times better at remembering sequential information, why isn't every tech giant throwing out their multi-billion-dollar transformers and building CMPs today?
Because, as with all true scientific breakthroughs, the devil is deeply embedded in the details. And to Arcadi Labs' immense credit, this paper is incredibly transparent about its limitations.
They didn't hide anything.
No, they dedicate a significant portion of the paper to reporting what they call honest negatives.
Let's go through those caveats because they are fascinating. Let's start with the order of the domains. Does it matter what sequence it reads those 15 data sets in?
It matters significantly. That jaw-dropping score of 0.1482, that was achieved using their canonical ordering, which was essentially their best-case scenario.
Okay.
When the researchers ran a rigorous domain order control where they reversed the sequence or shuffled the domains randomly, the forgetting increased. The BWT score ranged up to positive 0.4442.
Okay, let's put that in perspective. Up to 0.4442. which is still roughly 5 times better than the transformer armed with EWC.
True.
So it's still vastly superior, but it proves the system isn't perfectly immune. The sequence of learning still impacts the physical structure of the memory. But there's a much bigger hurdle keeping this out of commercial products right now, and that's the accuracy gap.
Yeah, the raw predictive power. CMP fundamentally is not more accurate than a transformer in raw single-domain prediction.
So if it's just doing one thing.
Right. When it comes to just guessing the very next byte accurately on a single, isolated task, the transformer beats CMP by a substantial margin. The paper explicitly states they are not claiming general superiority over attention-based architectures. CMP intentionally trades raw accuracy for structural memory retention.
And it wasn't just text they tested it on. They wanted to see if this forgetting resistance held up across different modalities, like computer vision.
Yeah, they ran a widely recognized benchmark called split MNIST, which turns images of handwritten digits into sequential learning tasks.
And how did it do?
The result was a pure, unmitigated null result. There was absolutely no measurable advantage for CMP's sparse weight protect system over a dense, standard neural network on vision tasks.
None at all.
None. The performance confidence intervals across their test runs overlapped completely. Statistically speaking, any difference was just noise.
Plus, they voluntarily admitted to a completely unresolved failure in the architecture. They realized they had that raw accuracy gap we just talked about, so they tried to combine CMP with a separate depth line mechanism to boost its predictive power.
And adding that feature actually made the model perform worse.
The mechanics of that failure are highly revealing, though.
They really are. The depth line mechanism relied on dense vectors. When they injected those dense vectors into CMP, it completely broke the delicate, sparse, slot-matching memory we discussed earlier.
Because it filled in the blanks on that spreadsheet.
Exactly. The density caused the concepts to overlap and smear together, destroying the memory protection.
This raises a crucial question about modern scientific publishing. Why dedicate precious page space to outline these failures so thoroughly?
Because it builds profound trust. In a world completely saturated with AI hype, where every tech press release claims to have definitively solved artificial general intelligence, an honest negative result is infinitely more useful to the engineering community than an omitted one.
So true.
By stating plainly what does not work, they make their central successful claim about forgetting resistance incredibly robust and credible.
It allows the field to build on real foundations rather than chasing marketing claims.
Exactly.
So, what does this all mean for the future of the technology? Let's synthesize this journey. We just explored a state-of-the-art paper that successfully challenges AI's absolute reliance on backpropagation.
A huge deal.
By throwing out the global, sweeping updates of modern transformers, and instead using sparse relational binding, a competitive two-tier memory, and a gradient-free weight protect throttle, CMP mathematically proves that local learning can structurally resist catastrophic forgetting up to 19 times better than our current best models.
Even if it currently has to trade off some raw predictive accuracy to pull it off.
It is a fundamental rethinking of how machines should learn over the dimension of time, and it forces us to reconsider the trajectory of AI development.
Definitely. If backpropagation is structurally doomed to forget, and local learning is the only mathematically proven way to retain sequential knowledge, we have to imagine a very different future.
And that leads to a fascinating thought experiment. Right now, to make an AI smarter, a tech company has to freeze the model, take it offline, and retrain it on a massive server farm with trillions of words just to update its knowledge base.
Which is horribly inefficient.
But if we eventually perfect this architecture, if we truly cure AI of catastrophic forgetting without sacrificing accuracy, it means models won't just learn in a sterilized laboratory anymore.
No, they could learn continuously, right on the edge, like in the devices we use every day. Biological brains don't use global backpropagation, right? They use local sparse updates, much like CMP. So maybe the true artificial general intelligence of the future won't look like these massive, power-hungry transformers. Maybe it looks more like this patchy, local learning, memory-protecting architecture we just broke down.
Exactly. What happens to society when an artificial intelligence can continuously learn in real time from every single unique conversation it has with every single human on Earth forever without ever overwriting what it learned yesterday?
It's mind-boggling.
an AI that organically grows alongside human society, rather than being periodically updated like a piece of static software. That is a radically different technological landscape than the one we are living in today.
It bridges the gap between static computation and genuine evolving cognition.
That is something to seriously chew on as you watch the AI headlines roll in this week. Thank you for joining us on this deep dive into the architecture of memory and the bleeding edge of machine learning. As always, keep questioning the structure of the information around you, and we will see you next time.